Alright, so 4.2 we're looking at maximum and minimum values. When we look at a function, and oops, sorry, here's your textbook. When we look at the function, there's a graph of function, just some random function f here. And what the textbook says is that notice that there are some high points, you know, and I would say locally high points, and some locally low points. That is, if you just consider the region right around, you know, in this section of the graph, you have a low point, and that's called a local minimum. That's what this low point would be, a local minimum. This would be a local maximum, local, okay? Now, the absolute largest y value in all of the values shown in this graph would be 6, okay? So we have 1, 5, 3, 6, 2, right? So the largest y value is 6 here. And we would look at this graph and we would say that the absolute highest point on the graph here looks to be y equals 6. Is that agreed? So that's what they call an absolute maximum. It's 6. And where is it? It's at x equals 7. And so this part of the description here, the absolute maximum is at x equals 7, and the absolute maximum value is 6. Right? The absolute minimum value, if you look at all of the points on this graph, the absolute lowest one is not this one or this one, but it's this one over here. Everyone see that? Given a graph, you can take a look and see what the absolute max or min is. Especially if there's an end, if there are end points, you can just take a look at the graph. So if we go back to our notes and I just draw you, you know, some random graph here, and I'm going to throw a little wrench in it here. Okay, let's say this is our graph, you know, f of x. Okay? And I say, okay, well, where is the absolute maximum here? You would say, okay, a maximum, we're looking for basically where the graph reaches the highest point. Okay, so this could be, okay, the absolute maximum, but looks like there's a higher point right about here. So do you see how that's a larger y value? So this right here, this point would be the absolute maximum. Okay? Now, if we're talking about an absolute minimum, we have a bit of a problem, because you may say, well, of the graph that I can see, it looks like this is a low point, but this is even lower. But then you might ask yourself, well, what about all the y values like over here? Because obviously this graph goes down and down and down. And of course, with the arrow means it goes down forever and never stops, right? So there's no beginning point. And so what we would say is that there is no absolute minimum here. And it's due to the fact that we have this arrow, and that means it extends down, and a little bit slightly looks like to the left, forever and ever and ever. So we wouldn't be able to identify an absolute minimum. So yeah, so we'll say that there's no absolute minimum. The question was, can we say the absolute minimum is negative infinity? And I guess my answer for now is we're going to stick with this, because when we talk about an absolute maximum, we are referring to a value, okay? And if we say the absolute minimum in this case is negative infinity, we're basically giving negative infinity a value, which doesn't make sense. So there is no value of negative infinity. It's not a value. So we won't say that. I don't know if you'll ever see that. You might see that someday, but it would be better to say there's no absolute minimum here. Okay, the other thing that I should tell you right now, because I have mentioned it in class here, is this right here is not an absolute maximum, but this is called a local maximum. And we'll talk a little bit more about local maximums and local minimums later, but if we're detailing a diagram here, we may as well write that. Now, the difference obviously between absolute and local means that absolute is considering the entire graph. Local is just considering all the points right around this maximum point. So you see, if I were to blow this up, right, this just maximize this here, maximize it. If I were to blow it up, and I just considered this part of the graph, You see how all of the other points around this point, all of the other points would have a lower y value. So that would mean that this is a local maximum compared to everything else right around it. And the reason why we're going to name those, and those are important, is because of what we're going to talk about next. Now, at local maximums, and this, you could consider this a local maximum and the absolute maximum for the function. But at local maximums, how can you give me a sentence that includes the words local maximum and derivative? Anybody want to take a stab at that? What's the connection there between a local maximum, let's say, and derivative? Or you could even think about the local minimum as well. Anybody want to try venture a guess? Okay, yes, very close. The derivative at a local maximum would be 0. Yes, you could say that, absolutely. No, I mean locally. I mean, whatever. I said absolutely you could say that, but absolute, it's a bit of a joke. Teacher joke, did you get that one? Okay, sorry. Absolutely, absolutely you're locally correct. Yeah. Yeah. If I just say congratulations, you're locally correct, it doesn't really mean, much. Okay. But yes, no, you're right. The exception would be, and I haven't covered this yet, but the exception would be if we have, let's say we have local maximums or minimums for a graph, but it looks like this. This would be a graph of an absolute value function, right? What it is it's sort of a line that gets reflected, right? So, and it's been obviously translated over and up. But this would be an absolute value function, and it is important to note two things: that this definitely is a local minimum. Excuse me. And given the fact that we have arrows here on either end here, it's also an absolute minimum for this function. Does everyone agree with that? You see that? But the thing is that the derivative at this point, at whatever point this is, we'll name it C, the derivative here is undefined. It doesn't exist. And I haven't talked about this yet, but I do want to talk about it now. If I overlay here a parabola, and remember, let's say this is the lowest point here. Remember how we found, limits. Okay. So let's say the derivative at this point is this. The derivative here is this. The derivative here is this. You can see that the values of the derivatives are getting pretty close to what? At this point, the value of the derivative looks like it's approaching 0. Okay. And it is, and we talked about that in the last question, okay? Derivative of 0. But with absolute value functions or graphs that have something called a cusp, like this, okay? This would be a cusp. Whoops, I don't know why I did that P like that. Cusp, sorry. I don't know what I was drawing there. And that would happen, when would this happen? Well, this would happen if we're talking about absolute value functions of parabolas, right? So let's say this is an absolute value function of a parabola. Wow, skills, hey? Okay, so at this point it would look sort of like this. This is kind of blown up. Alright? That is called a cusp. How many of you have ever had braces or have dental work done and you've ever heard the word cusp? Bicuspid, cusp. It's kind of at the point of the tooth there. Okay? No? Alright, fine, whatever. Anyways, this is called a cusp. And technically, the derivative does not exist there. Why? Really quickly, what are the derivatives leading up to this point? Well, from the right, the derivative would be the slope of this line. Right? Exactly the same as we get infinitely close to C. And then, boom, as we pass over C, it changes to this slope. So over here, we can see the slopes are gradually kind of moving towards this limit. But here, it's like, let's say this is a slope of 1, okay? So it's like right here, it's slope equals 1, slope equals 1, slope equals 1. All of a sudden, boom, slope equals -1, slope equals -1. You know what I mean? It's like, where is the limit there? There is no limit. So, I guess my whole point is local minimums and maximums will occur where, yes, what you said, where the derivative for the function is 0. That's a good guess. But also where the derivative doesn't exist. There may be a local max or min. All right. So if you look in your textbooks here, let's check the text now. Okay. So let's keep moving on here. So here's the local. So we're talking about local max or relative max. It also is relative. Local minimum or relative minimum. All right. So in this picture, a local minimum right here. This picture, no local min or max. Even though it looks like there might be a local maximum here, it doesn't ever turn back around. So there's no local min or max there. All right, these ones here, local max, local min. Endpoints, okay, that's a maximum, but you know, it's not really easy to say what happens with the derivative there. But in this diagram right here, you see that at f of a, okay, f of a is a local maximum. At b, f of b is a local minimum, local max. Now this is a local min and this is a local max, even though the derivatives are undefined at those points. This is my point. And that leads us to Fermat's theorem. Okay? Not Fermat's last theorem, but one of Fermat's theorems. And you want to write this down in your notes. If f function has a local minimum or maximum at c, then what's happening there is either f prime of c is 0 or it doesn't exist. So just take a moment to absorb that and look at this diagram as well. The x values that are associated with these maximum or minimums, I'm just going to say max or min, are called critical numbers. So a critical number is defined then as this. F prime of c, if that's 0, if the derivative is 0, then we have c a critical number. Or if f prime of c does not exist, then that's a critical number. Okay. So critical numbers will be referred to quite often here now. And if we look back to our sign analysis, so if you get that down, if we look back to our sign analysis, okay, this is the derivative, right? And guess what? At this x value, the derivative is 0, so guess what? What do you call this? This is it's a critical number. Critical number. This is a critical number as well. This is a critical number. So there are 3 critical numbers for this example. Right, so erase that now. Okay. Any questions? Max min values. All right. So mostly for today, it's this terminology. So going back to the absolute max and min, if you're asked to find an absolute minimum or an absolute maximum value for a function that is continuous on a closed interval, so that is where there are endpoints, then this is how you do that. First of all, you find the values of f at the critical numbers. So find the derivative and find out where the derivative equals 0. Those are the critical numbers. And then you evaluate the function at those critical numbers. So let's say you found the derivative of a function and you found a critical number at 2 and 4. then you would find f of 2 and f of 4 to find out what the y values are associated with those. And you would also find the values of the function at the endpoints and evaluate f of a and f of b. When you compare those, the largest of the values that you found in step 1 and step 2 would be the absolute max, and the smallest would be the absolute min. So just going back here, I'm just going to make note of this. Find the critical numbers and then evaluate f of c, however many critical numbers there are. And then do f of a and f of b. And between all of these values, the largest one is the absolute max and the smallest is the absolute min. So I would like to take you back just to, the very first page there, right here. So if we look back at this function here now, okay, this is number 4 here. 4, the x value 4, is a critical number. And 5 is also a critical number. And 7 is a critical number. So 4, 5, and 7 are the critical numbers for this function in this interval. You want to find f of c1, that is 5. And you find f of c2, that's 3. F of c3, that's critical number 3, and that's 6. You also find f of a, which is your endpoint here, and that's 1. F of b is 2. You take a look at all of these y values, 1, 5, 3, 6, 2. The smallest one is your absolute minimum. The largest one is your absolute maximum. Make sense? Okay. Alright. So yeah. The critical numbers are x values. The maximum values are the y values. Yeah. And when you say I have an absolute max, so for example, when you look at this example here, you have A is 2, right? That's the beginning point. B is 9. That's the end point. You've also found, let's say you did the calculus here and you found the critical numbers, or you look at this graph and you say, hey, I have a critical number is 4. The critical number here is 5, and the critical number here is 7. And so you evaluate f of c1, put it in the function, and here is 5. And so on. F of c2 is 3. F of c3 is 6. So then you consider all of these y values, and you find out whichever one's the largest one is the max. So the absolute max, what you'd say absolute max is 6. Okay? But you would say, you should write it like this. And it's displayed in the book too. Absolute max is f of 7 equaling 6. And the absolute min is f of 2 equals 1. For that particular example. Alright, so here's an example from the text that says find absolute max and min of this function. Here are the endpoints, so it goes from negative 3.5 to 1. We're not going to graph it, we're going to do the calculus to see if we can figure this out. Right? So f prime of x equals 3x squared plus 12x plus 9. We need to factor this and find out where the zeros are of this derivative. Take out a 3, that's x squared plus 4x plus 3. Factor that, that's x plus 3 and x plus 1. So the zeros, or the critical numbers, are, can you see from this row right here? Take a look at the factors. What x values will make this product 0? Negative 3 and negative 1. Okay? Good. What about 3? What about 3? This 3 right here? Okay, what x value will make 3 equal to 0? It's a tricky question, isn't it? X equals 3 will not make 3 0. x equals 3 will make this 6 and this 4. So you have 6 times 4 is 24 times 3 is what? Not 0, right? So because there's no variable here, there's no critical number attached to this factor. It's just a constant, yeah. So you just look at the factors that have variables. It's a good question. It's a very good question. I'm glad I was able to give you that answer. I didn't know anyone was thinking that. Okay, so let's do our sign analysis. So let's include 3 because it's a factor. And x plus 3, x plus 1. And I just want to show you here, because you don't have to do sign analysis for this, but I just want to show you, and if you've started this already, great. If you don't want to copy this down, I don't care. But 3 is always positive, right? X plus 3 is 0 at x equals a negative 3. So do you see how the critical numbers show up on the number line here when you do sign analysis on the derivative? And so you do this, and negative 1 over here, it's 0. So yeah, the zeros on the sign analysis are the critical numbers. So 3 and 1, and here's 3, and here's 1. Now for the next section, okay, we're going to be exploring sign analysis of the derivative further to get more information. But for now, this question just says find absolute max and min. So from what we know here so far, we need to evaluate f of, my endpoint is negative 3.5. I need to find out what that is. I also need to find out what my other endpoint is, f of 1, right? And I need to find out what f of negative 3 is and f of negative 1 is. Once I do that and find those values, plugging these x values into the original function, I just pick the largest one for my absolute max and the smallest one for my absolute min. Okay? When we evaluate these points, we have these numbers. Obviously, the maximum value is at x equals 1, which is one of the endpoints, right here. So you'd say absolute max at f of 1 equals 18. And I don't care if you abbreviate absolute max and min. That's no problem. So what's the minimum value here? There's 1.1, there's 2, there's negative 2. So f equals, or f at negative 1. Negative 2. Okay, that's what the math says. Now, I did graph it over here, and this is the graph right here. The endpoint, the leftmost endpoint there, negative 3.5, is right here. So you can kind of see, it's a little tough to see there, but it's not the lowest point, it's not the highest point. Right, so it shouldn't be the lowest point or highest point, and it's right here, so that makes sense. At this point right here, it looks like we have a local maximum. That's at 1, 2, 3, at negative 3. Well, look at that. We figured out we had a critical number at negative 3, and it is a local maximum. At negative 1, it looks like we have another critical number where the derivative looks to be 0, and look at that. We calculated negative 1 to be a critical number. And then at f of 1, so x equals 1 here, it's really, really, really high. It's off the charts here. And so that looks like it would be our absolute max for this domain, and we're correct there. All right? So that's how you find the absolute max, find the critical numbers, evaluate the function at the critical numbers and at the endpoints, and then take the largest and smallest number.